Hi everyone, welcome back to another Banach Space webinar. Today we are thrilled to have Gilles Lancien from Besançon, and he's speaking on Kalton's interlacing graphs and embedding into dual Banach spaces. Gilles?
Okay, so hello everyone, and thank you very much, Benjamin, for the invitation and for organizing this webinar every week. So today I will speak around a joint work with Bruno Braga, Colin Petitjean, and Tony Prochaska. And the general motivation of this work comes from two very important results. The first one is due to Aharoni, who proved in 1974 that every separable metric space Lipschitz embeds into C0, the space of scalar sequences tending to zero with a subnorm. In other words, C0 is a universal space for separable metric spaces and Lipschitz embeddings. The second result is due to Nigel Kalton in 2007 and goes in the other direction and says that if a Banach space contains a coarse copy of C0, and a coarse embedding is a weaker notion that I will define later, then this Banach space cannot be reflexive. Okay, and the main ingredient of Kalton's proof is a special family of metric graphs that we will call the Kalton's interlacing graphs. And I will focus on their embeddability into dual spaces. So it's now time to give some precise definitions. And I will introduce various notions of embeddings. So consider a map between two metric spaces, M and N, a map F, and we define its compression modulus and its expansion modulus. And you can read the formal definition if you wish. What you really have to understand is that they are essentially the best functions such that this uniform control is true. That is, the distance of the images is controlled by the two functions of the distances between x and y. Of course, they could very well be trivial, like omega could be infinity and rho could be zero. Okay. Now, what is a Lipschitz embedding? So as you know, it's a map which is Lipschitz one-to-one and with a Lipschitz inverse. So in terms of these moduli, you can define it as the expansion modulus is bounded above by a linear function, and the compression modulus is bounded below by a non-trivial linear function. Actually, I will be more interested with the notion of coarse Lipschitz embedding. Then it's a little bit weaker. We ask that the expansion modulus is bounded above by an affine function, and the compression modulus is bounded below by a non-trivial affine function, meaning that A is strictly positive. Okay, one important feature of this notion of so-called embedding is that it is not one-to-one. We don't assume injectivity, and actually we only care about large distances. In fact, another way to define it is to say that a coarse Lipschitz embedding is bi-Lipschitz for large enough distances. So you can see that if T is large enough, you can kind of forget about D and about C. All right. And the last notion is even weaker. It's a notion of a coarse embedding, which means that the expansion modulus is non-trivial, it's always finite, and the compression modulus goes to infinity at infinity. So if you go back to this inequality, you have this uniform control, which is especially interesting for large distances. Again, it does not say anything about injectivity, and large distances are mapped into large distances, essentially. That's the assumption that rho is going to infinity at infinity. So it's kind of preserving the geometry of the metric space, but in a very, very weak sense. Okay, now last definition, sorry. A family of metric space equi-coarsely embeds into another metric space. And the definition is essentially what you can expect, which is there are two functions, two control functions, omega and rho, satisfying those properties. Rho goes to infinity at infinity and omega is finite. And a family of maps from mi in n, such that rho of fi is bigger than rho and omega of fi is less than omega. So it's a kind of, yes, equi-coarse embedding. That's just what it means. So let me go back to Aharoni's theorem. So as I said, every separable metric space, Lipschitz embeds into C0. And there is a big open question around that, which is called the question or the problem of the converse of Aharoni's theorem, which is the following. If a Banach space contains a Lipschitz copy of C0, does it contain a subspace, a linear subspace, which is isomorphic to C0? This is an open question. But still, we can say something about such a space. There are differentiability results that ensure that if a map is Lipschitz from, say, a separable Banach space to a Banach space with a Radon-Nikodym property, then this map must have points of Gateau differentiability. And of course, if the map was from the beginning a Lipschitz embedding, this Gateau differential is going to be a linear embedding. And so C0 would be isomorphic to a subspace of a space with a Radon-Nikodym property, which is not true because C0 fails the Radon-Nikodym property. Okay, so in particular, and I will be interested with that, such a space cannot be a separable dual. And so one of the goals of this talk is to have similar statements for weaker notions of embeddings. So the second problem is now about coarse embeddings. What can we say about Banach spaces that are coarsely universal or equivalently containing a coarse copy of C0? So it was open for some time to know whether such a space could be reflexive. And Kalton answered this question in 2007. And he proved actually that if, let's say, separable Banach space contains a coarse copy of C0, then one of the iterated duals of X is not separable. So if you take X star, X double star, X triple star, at some point this will become non-separable. And he couldn't tell when. But at least this implies that the space cannot be reflexive. Okay, so here is a problem which could be named like, can we improve Kalton's result? So of course, the ultimate improvement would be to show that C0 cannot coarsely embed into a separable dual. So that's the first question, but a very natural one is also, can we embed C0 into a space with separable bidual? C0 has a non-separable bidual, so the question is quite natural. And the last one is more rhetorical. Can we find a universal n in Kalton's theorem? This is also open, I believe. Okay, but just one last remark here is that at least we cannot prove, because this is false, that such a space must contain a subspace linearly isomorphic to C0. And the example comes from the theory of free spaces. So we have heard a lot about them recently. I'm not going to define them, but just explain the idea of this result. Okay, so you put a new metric on C0, which is given by the distance between x and y is the norm of x minus y to the power p for some p fixed between 0 and 1. So it's another metric, and C0 equipped with this metric is isometric to its free space. Okay, this is elementary. And therefore, C0 with the original metric embeds sparsely and uniformly via this power p into this free space. And actually, the result of the theorem behind is that the free space of this metric space has the so-called Schur property, which means that any weakly null sequence is norm converging. So of course, a Schur space cannot contain a subspace isomorphic to C0. Okay, so let me now introduce Kalton's graphs. And it's a very simple construction. So they are defined on, so consider M to be an infinite subset of N. And for a fixed K, I denote M to the K, the set of K subsets of M, and I insist on writing them in increasing order. So the meaning of those brackets is actually a reference to this increasing order. And this notation is for the set of all finite sequences, still written in increasing order. And now we introduce a graph structure on NK, which is defined as follows. We will declare that two sequences are adjacent or neighbors, if they are different, of course, and if they interlace. So if you can see me, it's exactly what it means. You either alternate N1, M1, N2, M2, and so on, or the other way around, M1, N1, and so on. So these are neighbors in the graph, and the distance between two general sequences is the length of the path of geodesic path between in the graph between those two sequences. Okay, so let me state a few elementary properties. The first one is a very simple formula for this distance, but if you want to prove it, you have to put some effort, but it's not completely difficult. So the formula is the following. It's a maximum over all segments in N of this quantity. So number of elements in N bar intersected with S minus number of elements of M bar intersected with S and absolute values. And this is a way, for instance, to extend the metric to the whole set of finite sequences where the graph structure is not clear. It's also very helpful to prove the second part of the statement, which is actually a way to see this graph in C0. So let me denote by Sn the summing basis of C0. That is, Sn is the sum of the EIs from I equal 1 to n, where EI is the canonical basis of C0, and define f of n1 nk to be the sum from I equals 1 to k of the Sni. Okay, so let me now do some French high technology and to have an idea of what is this embedding. Well, f of n1 nk is just this stairway going down, starting at k and going down by 1 at n1 and by 1 at n2 and finishing at nk. So this is it for French technology. And this is, I believe, the good intuition for this graph. That is, we are looking for, so Kalton was looking for the right witness of non-reflexivity in C0. And clearly Sn is a good witness of that, because Sn is weak star converging to an element which is in L infinity, but not in C0, okay? And so I just conclude this statement by saying that this map is a bi-Lipschitz embedding from the graph into C0. And actually the distortion is 2. All right, so let me now speak about another statement by Kalton, which is kind of disjoint from the first one, and which says the following. If X is reflexive, then there is a constant such that for any K and any map F from NK from this metric graph to X, which is Lipschitz, then there is an infinite subset of N. This means infinite subset, such that the diameter of F of MK is bounded by C times the Lipschitz constant of F. So this is really a very strong concentration result. Here you have a graph of diameter K. This graph, this subgraph, is actually isomorphic to this one. This is the same. It's what I will call a full subgraph. And it has diameter K, but then its image is concentrated in something of diameter C if the map was 1 Lipschitz, okay? So such a space is said to have property Q, and so the theorem is that every reflexive Banach space has property Q. And of course, if a Banach space has property Q, then the family of graphs cannot equi-coarsely embed into X, because this condition here forbids rho of K to tend to infinity. And I remind you that rho was the expansion modulus, and we want this rho to tend to infinity at infinity. And therefore, C0 does not coarsely embed into X. So a few examples that are not reflexive. Capital L1 and little L1 are known to coarsely embed into the Hilbert space. So they have property Q. It's not difficult to show that stable Banach spaces have property Q. So stable Banach spaces are Banach spaces where, if you look at the distance between xn and ym, and you do limit m, limit n, if they exist, then you can switch the limits. And it's an easy exercise to show that if you can switch the limits over ultrafilter, if you prefer, then you have property Q. Kalton also proved that the James space face property Q, and it's a curiosity that I wanted to mention, but still the family of graph does not equi-coarsely embed into the James space. It was a previous work with Cola and Tony. It's a bit technical, so I'm not going to speak about this today. I just wanted to mention it. And there is a problem related to that, which I could call the converse of Kalton's theorem problem. Does any Banach space with property Q coarsely embed into a reflexive Banach space? I think it's still open. Don't really believe it's true, but it's open. Okay, I'm going to speak about dual spaces, so I cannot help. I have to speak about the Szlenk index. And so why do I have to speak about the Szlenk index? Because we can characterize, and I will explain how, separable duals by properties of the Szlenk index. So let me try to explain what is the Szlenk index, and I will restrict myself to separable Banach spaces. And I will let's give ourselves K, a weak star compact subset of X star, the dual, and a fixed epsilon positive. Then this is defined with a Cantor-like derivation, and the derived set S epsilon of K is the set of X star in K that you can realize as a limit, as a weak star limit of a sequence in K, which is epsilon apart from X star. Okay, so you imagine a sequence which is weak star converging but staying epsilon apart. Of course, you cannot do that in finite dimension. This is empty if the dimension is finite. And then, like for the Cantor derivation, you iterate using ordinals, starting with K. For successor ordinals, you apply the derivation once more. And for limit ordinals, you take the intersection of what was defined before. And then the Szlenk index of X and epsilon is the first ordinal so that this is empty. So sometimes it's never empty. So we just say that it's an abstract infinity, which doesn't mean anything. So really what you have to have in mind is that the Szlenk index is counting how many levels of this occurrence, how many levels of sequences that are weak star converging and epsilon apart, how many levels you can build inside the unit ball. Okay, this is exactly what the Szlenk index is, and this could be an ordinal. Okay, and taking the supremum over epsilon positive is a nice way to get an isomorphic invariant. All right, so the key proposition here is a well-known fact, which is that for a separable Banach space, the dual is separable if and only if the Szlenk index is countable. Okay, so in some sense, the Szlenk index of X can be seen as a measurement of how close to be non-separable X star is. So of course, trying to show that a space containing C0, a dual space containing C0 cannot be separable, we will try to show that the Szlenk index of the underlying space is as big as we want. This is the idea. It was the idea of the starting idea of this work. So here is the first result I wanted to mention. And it says that if the family of graphs, of Kalton's graphs, equi-Lipschitz embeds into X star, then the Szlenk index cannot take the smallest possible value. So omega is the first infinite ordinal, and the smallest possible value for a Szlenk index in infinite dimension is omega. So at least we could say that it cannot be the smallest value. It was not satisfying. We tried very hard to push it further to higher ordinals, couldn't succeed, and for one good reason, which is that, in fact, it was optimal. That is, there is a separable Banach space with a Szlenk index omega squared, which is the next smallest possible value, because the Szlenk index is always a power of omega. This is a fact of life. And so there is a Banach space with a small Szlenk index and containing bi-Lipschitz, the whole graph, actually, of all finite sequences. All right, so before to give an idea of the proof, at least of theorem 1, I wanted to comment a little bit on some improved version of theorem 1. We can say more than that, actually. And in order to explain that, I have to speak about a fundamental renorming theorem, which is due to Knaust, Odell, and Schumprecht in 1999. And they showed the following. So assume that a separable Banach space has a small Szlenk index, the smallest possible. I am not interested in finite dimensional spaces. So this is equivalent to the existence of P strictly bigger than 1 such that X admits an equivalent P-AUS norm. So AUS here stands for asymptotically uniformly smooth, and I'm not going to define it. This is equivalent to having a dual norm, which is Q-AUC star, where Q is the conjugate of P, and AUC star means asymptotically uniformly convex for the weak star topology. And here is the meaning of that. It means that there is a constant C, such that whenever you take a sequence in the ball of X star, a Szlenk sequence, that is, it is weak star converging to X star and epsilon apart from X star. So whenever you are in this situation, then you lose something on the norm of the limit point. Norm of X star is less than 1 minus C epsilon to the Q. So of course, if each time you take a weak star limit, which is epsilon apart, you have to lose something on the norm, you can only do it finitely many times. And this is the easy implication of this theorem. And actually, the theorem is the converse. If the Szlenk index is omega, then there is such a norm. Okay. All right. Now let me go back to metric notions and let me extend or weaken the definition of property Q. So the P here is still the same as in the previous slide. It's strictly bigger than 1. And we will say that space X has property QP if, so it's just the same, there is a constant, such that for any map from the graph and any K, there is an infinite subset, such that the diameter of this full subgraph is less than C times Lipschitz of F times, and this is the important change here, K to the 1 upon P. So this is a concentration property, but much weaker. All right. So note in passing that Q infinity is just property Q, when K to the 1 upon infinity is 1. All right, so the upgraded version of theorem 1 is the following. If X is P-AUS or P-AUS renormable, then X star has property QP. And of course, QP forbids equi-Lipschitz embeddings. Okay, it cannot be equi-Lipschitz because it's K1 to the 1 upon P here. And okay, so it's an improvement of theorem 1. Just a few comments about this. We see it as a new obstruction to coarse Lipschitz embeddings in some AUC Banach spaces. So the usual argument in this type of situation is the so-called approximate midpoint principle. So there is a big drawback for our statement here. It's only interesting in the non-reflexive setting, just because of Kalton's theorem. If your space is reflexive, everything has property Q, and you cannot say very much. Okay, but there are situations where you get more information with those graphs than you can get with the approximate midpoint principle, and this is the case for the James spaces. So I won't tell more about the James spaces, but you can really, the type of information you can get is essentially about what are called compression exponents of embeddings between two Banach spaces. And one remark about this statement, the spaces that are infinity AUS are exactly the subspaces of C0. I mean, up to renorming. And a consequence of this is that duals of subspaces of C0 have property Q. Actually, we can improve this, and I will tell more about that a little bit later. Okay, let me try now to give a sketch of proof for the first theorem, which is assume that you have a family of equi-Lipschitz embeddings from the interlacing graphs into X star. And well, I didn't mention it, but since those graphs are all one separated, equi-Lipschitz or equi-coarse Lipschitz is essentially the same. So you have a family of maps that are all one Lipschitz, we can assume that, and with inverse that are 1 over a Lipschitz. So we are going to extract a lot of subsequences. So the first step is to, and I will need to give a lot of explanations here. The first step is a reduction to decompose the map F. So by passing to an infinite subset of n, I claim that we may assume that there is a weak star null tree. So it's I will explain what is a weak star null tree. It's indexed by all sequences of length at most k. And this weak star null tree is a way to reconstruct the function. Like for a sequence of length k, f of n bar is the sum for all predecessors of n bar of x star of n bar. So you can imagine you have this tree, and the image of a point on top of the tree can be reconstructed with the elements on the branch. And also there is an estimate on the norm of these elements, at least except for the root of the tree. All right, so what do I mean by weak star null? Weak star null means, for instance, you start with x star of m1, mk minus 1, mk. If you let mk tend to infinity, I want this to tend weak star to 0. And then, if you let mk minus 1 tends to infinity in x star of m1, mk minus 1, again, this will tend weak star to 0. So each time you go from one level to the next, it's weak star converging to 0. This is the meaning of weak star null. So how do we construct this weak star null tree? Well, we are in a separable, we are in dual of a separable Banach space. So we have weak star compactness. So we can extract weak star converging sequences. So if I assume that I have extracted sequences, so up to extracting subsequences, when nk goes to infinity, this has a weak star limit. I should have written weak star here. This has a weak star limit that will only depend on n1 and k minus 1, and that I will call df. Okay, and again, this in turn has a weak star limit that will only depend on n1 and k minus 2, and so on. And so what is x star of m bar now? Well, you make the differences. So x star of n1 nk is a difference between those two terms. And x star of n1 nk minus 1 is a difference between those two, and so on. And so when you reconstruct f, it's a telescopic reconstruction that gives you that f of m bar is the sum of all these differences. Okay? And this makes these differences weak star null, just by construction. And why are they bounded by 1? Well, just because the map is 1 Lipschitz. And you use the definition of the distance, the fact that the norm is weak star over semi-continuous, and you get that the norm is less than 1. So this is the first step. Then we are going to extract further subsequences, but this is now quite routine. So the norm of those elements, they live in the compact interval 0, 1. Okay, so which means that by a Ramsey argument at a given level I, they almost stabilize up to a small approximation that you fix at the beginning. They are almost constant in norm. Okay, I forgot to put a star here. So essentially, you can assume that at each level, the norm of x star m bar is constant. But the constant has to depend on I. And this is just a consequence of Ramsey's theorem. And the last reduction is, well, imagine that instead of taking 2 to the ni plus 1, I consider something going to infinity here. So this is weak star null. So this difference is tending weak star to this element, which is of norm ki. And by properties of the weak star topology, the limit of the norm as this tends to infinity is at least ki. So meaning, if I go far enough or extract, I can assume that I have this inequality. All right, until now it was just routine, and the main idea of the proof is now. So let me define for a given n bar of length I, y star of n bar to be this difference between the sequence of even numbers, 2n1, 2ni, and this sequence of odd numbers. Okay, and then I construct a new tree by putting z star of n bar to be the sum for all predecessors of n bar of y star of n bar. Now, this is again a tree. It's indexed by this set. And now it's weak star continuous. By weak star continuous, I mean each time I take a weak star limit from one level to the next, well, I get to the next level. From level k, I take weak star limit. I have the value at level k minus 1, and so on. Okay, but this is not the most important thing. What is important is that this weak star null tree is in the unit ball of X star. And the reason is very simple. If you look back, z star of n bar is just for an n bar of length k. It's exactly f of 2n1, 2nk minus f of 2n1 plus 1, 2nk plus 1. Just look back here, summing all these differences give you exactly what you expect because of I, okay? And those two sequences, they are interlaced. So they are at distance 1. And because the map is 1 Lipschitz, you get this estimate. So we have a weak star null tree, a weak star continuous tree inside the ball. So we are very close to apply the definition of the Szlenk index. And we need one more argument here. Now we consider two sequences, n1nk and m1nk, which are in the complete opposite situation, which is n bar is completely before n bar. So those two sequences are at distance k, okay? And so ak is less than f of n bar minus f of n bar, which is less than the sum of the norms, which is less than 2 times the sum of ki's, because f of n bar is what, because of the assumptions we had. And now it's very easy. You just count, you are just going to show that there are many i's such that ki is big. So let me denote n the cardinality of the set of i's such that ki is bigger than a over 4. Then what is written here is that ak over 2 is less than the sum of the ki's. And in this sum, you have terms that are less than a over 4, but at most k of them, plus n terms that are less than 1. So finally, n is bigger than ak over 4. And from this, you deduce that 0 is in the derived set of order n, because what did we do? At least n levels, I don't know where, but at least n levels, ki is bigger than a over 4. So at least n times, I go down one step further in the Szlenk derivation. And this proves that the Szlenk index of x has to be bigger for epsilon equals a over 4, has to be bigger than ak over 4. And if this is true for any k, this is the end of the proof. Okay, well, I still have 10 minutes, I believe. All right, so with the same proof, we can actually say a little bit more. Let me introduce the notion of summable Szlenk index. So summable Szlenk index is a kind of the quickest Szlenk derivation you can imagine. And this is well, let me say it backwards. Anyway, the sum of the epsilon i's is bigger than C, then you are sure that when you do the epsilon 1 derivation, then the epsilon 2, then the epsilon n, this is empty. Okay, it implies that the Szlenk index is proportional to 1 over epsilon, but we don't know if it is equivalent, I think. All right, and just look at the proof that I explained, and you copy paste, and you have a proof that if a Banach space has a summable Szlenk index, then X star has property Q. And so for specialists, having a summable Szlenk index is equivalent to being asymptotic C0. And I think this is a result of Ryan Cozy. And there are many examples of such spaces that are not subspaces of C0, that are not reflexive. There are people in the audience that can build asymptotic C0 spaces with only one hand, no foot, in any situation. Okay, so I just wanted to mention, and I realized this question when I was preparing the talk, which is a kind of a sub-question of the question of the converse of Kalton's problem, or Kalton's theorem. I don't know, at least, if any dual of an asymptotic C0 space can be coarsely embedded into a reflexive Banach space. This could be nice. All right. Okay, so I believe I still have a little bit of time, and I wanted to give you an idea of the proof of the optimality. So the plan of the proof is very simple. You look at this metric space. It isometrically embeds into its free space, like any metric space. And the goal is to prove that this free space is actually isomorphic to a subspace of a dual, where the underlying X has the small Szlenk index. So this is how the proof goes. And let me go back to the summing basis of C0. And we will actually use the image by F, of this graph rather than the graph itself. Okay, and so let me denote MK, the image by this function of the graph. And I recall that this is 2 Lipschitz equivalent to our initial graph. And let me denote by PK the weak star closure of MK in L infinity. Okay, so this looks simple. It is also very simple to check that one can describe the weak star closure of MK like this. It's made of some finite sums of SNIs plus multiples of the constant function equal to 1 with the condition of that J plus L is at most K. Okay, this is not difficult. So what is very important and crucial here is that this metric space is bounded, countable, uniformly discrete, meaning here every two different points are at distance at least 1, and weak star compact. So it's weak star compact for a topology for which the norm is weak star is lower semi-continuous. This is very important. And under these assumptions, there is a very nice result by Luis Carlos, Colin, Tony, and Abraham that ensures that the free space of PK is isometric to a dual space, xk star. And this xk, the pre-dual, is the space of Lipschitz function on PK, vanishing at 0, that are also weak star continuous. but very important, it is equipped with the Lipschitz norm. All right. Next step is, again, to use another paper of Kalton, which says that for any metric space, the free space of a metric space is linearly isomorphic to a subspace of the L1 sum of its dyadic balls, of the free spaces of its dyadic balls. So using these two Lipschitz equivalents, we have actually that f of m is linearly isomorphic to a subspace of the L1 sum of the free spaces of the M2Ks. And therefore, in the L1 sum of the free spaces of the P2Ks, which is the dual of the C0 sum of the X2Ks. So our space X is this space. And now what we want is to show that the Szlenk index is not too big. And this is very quick. Pk is bounded, uniformly discrete. So actually, when you equip the Lipschitz norm here, is actually equivalent to the subnorm. So this space is isomorphic to a subspace of the space of continuous function, of weak star continuous function on Pk, which is a compact with the subnorm. And then the counter-Bendingson index of Pk with the weak star topology is finite. It's another easy exercise. And it follows that xk is actually isomorphic to a subspace of C0. And which is due, I guess, to Besagal and Palczynski. Okay, of course, the isomorphism constant is exploding when we are doing this, but this is enough. We can conclude that the Szlenk index of xk is omega, and therefore the Szlenk index of x cannot exceed omega squared. It's another fact of life about the Szlenk index. All right, what time is it? Oh, maybe I have 2 minutes for the last slide. Well, I will just state results about embeddings of C0 with extra assumptions. So the first one says that if you ask if C0 coarse-Lipschitz embeds into a dual space, and you ask that the coarse-Lipschitz distortion, which is a quotient of A and B and the definition of coarse-Lipschitz embeddings, is not too big, that is strictly less than 3/2, then X star is non-separable, and even more than that, X contains, must contain a copy of literal L1. Another direction, you cannot embed coarsely C0 or L1 into a separable dual with a map that is weak to weak star sequentially continuous. So if you combine this very nonlinear assumption with something which is more linear, and speaking about weak topologies, you find a contradiction. And I wanted to mention something that we noticed in another work with Florent, Pavlos, and Thomas, putting together a number of results by Kalton. There is the following important thing, which is if your Banach space is a Banach lattice, then you have a very strong result that if a Banach lattice equi-coarsely contains Kalton's graphs, then X must contain a subspace which is isomorphic to C0. Okay, well, I believe I'm done, and thank you very much for listening.
Yeah, thank you very much, Gilles. That was a wonderful talk. So we can open for questions. If there are any questions or comments, please go ahead.
So, Gilles.
Yeah.
Can you go back to a few slides back? You had questions about duals.
This one?
Scientific C0. No, before. Yeah, 4B.
Yeah. So, right. So what is proved here is that the dual of an asymptotic C0 space has property Q. Okay. So the general question is, if a space has property Q, does it coarsely embed into a reflexive Banach space? And so what I want to do is to restrict this question to duals of asymptotic C0 Banach spaces.
But what about Searson? I'm missing something here.
Well, it's reflexive.
Yes.
Searson is reflexive.
You want a non-reflexive example? Okay.
Yes. So like little L1, for instance. Little L1 is an example. But you know, Thomas is hiding somewhere, but he can build asymptotic C0 spaces such that the quotient of the bidual with something is whatever you like.
Okay. Yeah, I misunderstood the question. Okay.
Okay, thank you. Any others?
Yes, please.
Go ahead.
Can I ask?
Sure, go ahead.
I was Kalton's contemporary at Cambridge. Now, one thing is, you know, you take L1 sum, can you take J sum, James sum? Because the, you know, second duals will be much smaller. That is one thing.
I'm sorry, I'm not sure.
In which theorem?
Just before the finishing, you took L1 sum, things embedding into L1 sum. So can you take a James sum?
Oh, in the proof of the Szlenk index estimates, yeah.
Yes,
so.
that is one thing. You know,
secondly, go ahead, yeah.
Secondly, most of your sequence spaces are already algebras under pointwise operations, and their duals are closed linear hulls of the multiplicative linear functionals. Most of the spaces that concrete sequence spaces that came by. So would it help to consider Banach algebras and X instead of just Banach space, and take algebra homomorphisms rather than just linear maps? Would that make things better or worse? I'm just curious, you know.
Oh, it would make life much more complicated, because you know, the whole idea is to get from the existence of a nonlinear embedding to a linear one. And so, of course, it will be even much more difficult to get something which has even more structure, more algebraic structure. So the starting point would be to, I'm not very knowledgeable about that, but first to know what is true about what is true if you know that there is a linear embedding. Is there something which is even better, like an algebra homomorphisms? Even that is not clear and probably very rare.
Okay, another thing is every separable Banach space is Jx double star by Jx. You know, you can take James sums of increasing sequence of Banach subspaces. Belenot did that in 1982 Journal Functional Analysis. Lindenstrass gave such a result. So every separable Banach space is quotient of a bidual by the space.
That's
so
true.
Does that help in any way to embed these spaces?
Actually, this is a very good remark. There is some hope. I don't know any result in this direction, but this is a very good suggestion. Like, you take Lindenstraus construction, and so, as you said, given X a separable Banach space, there is another Banach space Z, such that Z double star over Z is isomorphic to X.
Yes.
And of course, this space Z has special properties, and you would, I imagine, hope to embed X in some nonlinear way into Z.
Yes.
I think it's a very good idea. Yeah, it's a very good suggestion.
Thank you. Thank you.
Thanks so much for the question. Any other questions or comments? All right, if not, so thanks again, Gilles, for a beautiful talk. So I'm stopping the recording now.